Hello everyone, my name is Professor Oakes and this video is about the natural logarithmic function and its properties. So here are some of the basic properties of the natural logarithm. So the natural logarithm of a product, if a is greater than 0 and b is greater than 0, then the natural log of a times b is equal to the natural log of a plus the natural log of b. All right, so you have similar rules here for the quotient here. Then you have the natural logarithm of a rational power here. So that would be, well, if you think about it, actually, this is a redundant rule because it's actually the same as the product rule, because this would be x to the k would be natural log of, let's say it was x to the third, then it would be using this rule here, natural log of x times x times x. So that's natural log of x plus natural log of x plus natural log of x. So that would be 3 natural log of x. But because there's a pattern that would occur every time, the rule is that you can just take this exponent here and then bring it down in front to get k natural log of x. All right, so I just showed it for the one case of x to the third, but you could show this for any exponent. All right, so the monotonicity of the natural logarithm. So if a is a number between 0 and b, then the natural log of a is less than the natural log of b. And if x is greater than 0 and y is greater than 0, and the natural log of x is equal to the natural log of y, then it follows that x is equal to y. All right, so let's consider the function f of x is equal to the natural log of x minus 2. So let's sketch the graph, find the asymptotes and the intercepts, and state the domain and the range. So for f of x is equal to the natural log of x minus 2, this argument here has to always be greater than 0. So x minus 2 must be greater than 0, so that means x is greater than 2. So let's see, I know for sure then if I need to list the asymptotes and the intercepts and the domain and the range, well, the domain is already x is greater than 2, or 2 to infinity in interval notation. All right, so now let's go ahead and try to graph this, but one way to do that might actually be to find out what the intercepts are first. All right, so let's see if there is an x-intercept. And for the x-intercept, we know that where is it? Oh, the y has to be 0, so we have natural log of x minus 2 is equal to 0. So then we exponentiate each side, so x minus 2 is equal to e to the 0, which is 1, and then add the 2 to get x is equal to 3. So the x-intercept is at 3, 0. And we know that x has to be greater than 2. So there's an intercept at 3, 0. And x is greater than 2. So that means, of course, since x is greater than 2, that there can't be any y-intercept. And we also can tell, hopefully, that the asymptote here is going to be at x equals 2. And the range, well, the range does not appear to be restricted, so that will be negative infinity to infinity, all real numbers. All right, so now if you're not sure what to do, you can substitute some numbers in here into a table to figure out what the graph would hopefully look like. So if we have, again, 3, we got 0. Let's just try, let's go for 4. All right, so natural log of 4 minus 2 is natural log of 2, and that's about 0.6931. So 4.6931. All right, let's try 5. Natural log of 5 minus 2 is natural log of 3, so that's about 1.099. So that's a little bit over 1. Then 6. All right, natural log of 6 minus 2 is natural log of 4, so that's about 1.386. So now I can go ahead and draw this graph here. All right, so x-axis, y-axis. Now, by the way, if you really want to see, well, does this really go to negative infinity, as I'm showing, you could pick a number that's close to 2, like 2.001, and natural log of 2.001 minus 2 is natural log of 0.001, and natural log of 0.001 happens to be a negative number, about negative 6.908. All right, so I do know indeed that this is actually going to be negative and go to negative infinity at some point, even if it takes a little while to do so. All right, now for the second part of the problem, so this was all part 1, sketching the graph and finding the asymptotes and the intercepts in the domain and the range. So if I want to find the limit as x approaches 2 from the left of the natural log of x minus 2, well, this does not exist, right? So does not exist, and hopefully you can see that this doesn't exist because the function doesn't exist to the left of 2. All right, so the function doesn't exist to the left of 2. What a time to be alive. So hopefully you enjoyed that example here. So let's get ready for another example. So let's use the properties of logarithms to expand this expression here, natural log of x times the square root of y. Now again, you might be wondering, why are we doing this in a calculus video? But we might want to sometimes use some of these properties of logarithms to make finding the derivatives easier later on. So we'll get to that in a moment, but for now, try to remember the property for the product of the logarithms, and natural log of a plus natural log of b is natural log of a times b. So here's a, here's b. All right, so we have natural log of x plus natural log of the square root of y. But the square root of y is really y to the 1/2 power. And then remember the rule of natural log of x to the k, or x to some power, was k natural log of x. So I can rewrite the natural log of y to the 1/2 power as 1/2 natural log of y. What a time to be alive. All right, let's try another one. here we have a quotient, so natural log of A minus natural log of B is natural log of A over B. So here is A, here is B. So we have natural log of x minus natural log of x minus 1 squared. Then I use the power rule for the logarithms, and I can rewrite natural log of x minus 1 all quantity squared there as 2 natural log of x minus 1. And that's it. All right, so do not get any misconception here that you can actually break up the natural log of x minus 1, because there is not any rule for that. All right. There are other ways to write that, but not specifically to get rid of the difference there, or the subtraction there. All right, so now here are some examples of writing the expressions as a logarithm of a single quantity. So that means writing this back in its original form, and currently it's in expanded form. So we see here that we have the 3, the 2, and the 4. So I can write this as natural log of x to the third plus natural log of y squared, and then minus natural log of z to the fourth. All right, so I use the power rule in reverse. So use the power rule for logarithms. Now I want to be specific on that because we've had lots of power rules already, like power rule for derivatives and so forth. And now, let's see, we'll use the product rule. So there's a plus, so we can multiply this as natural log of x to the third times y squared minus natural log of z to the fourth. So this was the product rule for logarithms. Right now we see the minus, and now we're going to use the quotient rule for logarithms. So we'll have natural log of x to the third y squared over z to the fourth. What a time to be alive. So hopefully that all made sense of how to use the properties here to go in reverse. All right, so let's try again. So here you see a whole lot going on. So let's go ahead and work inside of the parentheses first, because that's what you would normally do. So we see the plus here. So I'm going to use the product rule and bring these two logarithms back together as a single logarithm, natural log of x minus 1 times y. All right. Then I see the exponents here, so the 3 and the 1/2. So I'm going to use the power rule for logarithms here. So power rule. So I have natural log of 2 to the third minus natural log of x minus 1 times y to the 1/2 power. Now let's just, because of all this going on here, just do the exponents first. So 2 to the third is 8, and the 1/2 power indicates the square root. So square root of x minus 1 times y. So then I see the minus here, and I'm going to use the quotient rule. So I have natural log of 8 over the square root of x minus 1 times y. What a time to be alive. I really hope that you enjoyed this example here. All right, so now it is time for the derivative of the natural logarithmic function. So the natural log of u. So if u is a differentiable function of x and u is greater than 0, then the derivative with respect to x of the natural log of u is 1 over u times the derivative of u with respect to x. So in other words, if u was just equal to x, then you have d dx of the natural log of x is 1 over x. All right, so here we go. If u is always the argument, x minus 1, then f prime of x is 1 over u times du dx. So u prime or du dx is the derivative of x minus 1, which is 1. So 1 over u, in this case, is 1 over x minus 1 times 1. So it's just 1 over x minus 1. All right, let's try again. So here we have a product. All right, so we are going to use the product rule for finding derivatives. So u will be x squared v natural log of x. So du dx is 2x, dv dx is 1 over x. So g prime of x will be, well, v du dx plus u dv dx. So that is 2x natural log of x plus x squared times 1 over x. And x squared times 1 over x then is just x. So it's 2x natural log of x plus x. Now, what a time to be alive. Let's try another example here. You have the y is equal to natural log of 2x over x plus 3. So u could be 2x over x plus 3. Then you need to use the quotient rule. So quotient rule. All right, so now I already used u, so the numerator, let's just use n for numerator, and that would be 2x and d for denominator, x plus 3. So dn dx is 2, dd dx is 1. So using the quotient rule, all right, so try to make sure that you know what's going on, all right? So y prime is 1 over u times du dx. So all I'm finding now is du dx. So that will be the 2 times x plus 3 minus 2x times 1 all over x plus 3 squared. So let's distribute the 2. So we have 2x plus 6 minus 2x all over x plus 3 squared. The 2x's zero out. So I have, what do we have? We have, well, we have 6 over x plus 3 squared. All right, so that's du dx. So 1 over u will be 1 over 2x over x plus 3 times du dx 6 over x plus 3 squared. And then I multiply by the reciprocal here. So I have x plus 3 over 2x times 6 over x plus 3 squared. X plus 3 divides out, a 2 divides out, so I'm left with 3 over x times x plus 3 as the derivative, which is y prime in this case. Now, let me just be absolutely clear on this fact that this would have been a quicker way to find this derivative. Y is natural log of 2x over x plus 3. I'm going to use the quotient rule for the logarithm first. To rewrite this as natural log of 2x minus natural log of x plus 3. Then I'm going to use the product rule for logarithms to rewrite this as natural log of 2 plus natural log of x minus natural log of x plus 3. Then I'm going to find the derivative. So y prime, so this is y, that's y, this is now y prime. The derivative of natural log of 2 is 0. The derivative of natural log of x is 1 over x. And the derivative of natural log of x plus 3 is 1 over x plus 3 times the derivative of x plus 3, which is 1. And then if I find a common denominator, I get x plus 3 minus x all over x times x plus 3. The x's zero out, and I'm left with 3 over x times x plus 3, which is the same derivative that I had using a much longer method. At least in my opinion, it was longer. All right, let's try another wonderful example here. The derivative of y equals the natural log of the absolute value of cosine of x. So y prime will be 1 over the cosine of x, right? And then the derivative with respect to x of the cosine of x is negative sine of x. And so then that means that this is just negative sine of x over cosine of x is negative tangent of x. All right, what a time to be alive. I really hope that you enjoyed that example as well. So now it is time for another example here, and this one will involve implicit differentiation here. So we want to find d dx of natural log of x times y plus 5x equals 30. So let's actually rewrite this as this part right here as d dx then of natural log of x plus natural log of y plus 5x equals 30. The derivative with respect to x of natural log of x is 1 over x. The derivative with respect to x of natural log of y is 1 over y times dy dx. Remember, we are finding the derivative using implicit differentiation here. All right, just as a reminder. All right, the derivative with respect to x of 5x is 5, and the derivative with respect to x of 30 is 0. So now I need to solve for dy dx, so I'll subtract the 1 over x to get 1 over y dy dx plus 5 is negative 1 over x. Then what I'll do here is subtract the 5, so 1 over y dy dx equals negative 1 over x minus 5, and then multiply by y to get dy dx is equal to negative y over x minus 5y. What a time to be alive. All right, here's another great example. Find an equation of the tangent line to the graph at the given point. So remember, the equation of the tangent line is y minus y1 is m times x minus x1. We know x1, we know y1. So we just need to find the slope of the tangent line, which means m is f prime of x. All right, so we need to find f prime of x here. So it really, as I've said this before, it doesn't matter how you go about finding this derivative here, but if you look at f of x equals 1/2 x natural log of x squared, I can use the power rule for logarithms to write this as 2 natural log of x, then 1/2 times 2 is 1, so I have x natural log of x. All right, then I can use the product rule. So u will be x and v will be natural log of x. So du dx is 1, dv dx is 1 over x. So that means f prime of x is v du dx, so natural log of x, plus u dv dx, x times 1 over x, which is, once the x's divide out, equal to 1, so natural log of x plus 1. Then if I want to find this slope specifically at the point 1, 0, I need to find f prime of x1 or f prime of 1, so that's natural log of 1 plus 1. Natural log of 1 happens to be 0, and 0 plus 1 is 1. So I know y1 was 0, and I know the slope at the point 1, 0, the slope of the tangent line at the point 1, 0 was actually equal to 1, and I know that x1 was equal to 1, so if I simplify this here, I have y is equal to x minus 1, and that is the equation of the tangent line to the graph of f of x equals 1/2 x times the natural log of x squared at the point 1, 0. What a time to be alive. I really hope that you are enjoying this section so far, because we're not done. We have the derivative of the exponential function now. So the derivative with respect to x of e to the x is e to the x. So if I wanted the derivative with respect to x of e to the u, then it would be e to the u, and then the derivative with respect to x of u. So just the chain rule, just as before. So the u will be the exponent. So if we want to find the derivative of y equals e to the negative x squared, the u is the exponent, and then du dx would be, in this particular case, negative 2x. So y prime is e to the u, so e to the negative x squared times du dx, which is negative 2x, and I'll rewrite it as negative 2x e to the negative x squared just to make sure I don't accidentally put this negative 2x into the exponent when I don't mean to. All right, so part B here, y is equal to x e to the x. I need to use the product rule here. So u will be x, v is e to the x, du dx is 1, dv dx is e to the x, so y prime is v du dx plus u dv dx. All right, so we have, well, that's e to the x times 1 plus x e to the x, or just, well, what do you want to write that as? Well, there's nothing else to say. It's e to the x plus x e to the x. All right, what a time to be alive. All right, here's another example here. The y is equal to the natural log of the quantity of 1 plus e to the x over 1 minus e to the x. So I hope that we learned our lesson in the last set of examples, that I am going to use some algebraic rules for logarithms first to simplify this expression here before finding the derivative. All right, so now that I've used the quotient rule for the logarithms, I'll find the derivative. So let's see, we have the derivative for natural log of 1 plus e to the x. So if u is 1 plus e to the x, du dx is e to the x. And over here, let's just call this, you can call it u1 maybe, or u2, because they should be separate. So 1 minus e to the x, then that derivative will be negative e to the x. So the derivative y prime then is, I'll move this down a little bit here. I don't know what that is. So y prime will be 1 over u, so 1 over 1 plus e to the x times du dx e to the x minus this minus. All right, so 1 over u, 1 minus e to the x times du dx negative e to the x. And now I can just leave this as e to the x over 1 plus e to the x, and then minus times minus is plus, so plus e to the x over 1 minus e to the x. If I wanted to find a common denominator, I could multiply this by 1 minus e to the x over 1 minus e to the x, and 1 plus e to the x over 1 plus e to the x. So 1 minus e to the x times 1 plus e to the x. I'll distribute, so I have e to the x minus e to the 2x, distribute, plus e to the x plus e to the 2x. E to the 2x zeroes out, so I actually have e to the x plus e to the x, which is 2e to the x all over 1 minus e to the x times 1 plus e to the x. What a time to be alive. I truly hope that you enjoyed that example because there's still more. So here is another one. And hopefully you can see that this example will involve some implicit differentiation here because there's especially in particular this x, y, and the exponent here. So we're going to use the implicit differentiation here. Or you could solve this for y, but I don't think you really want to. So d dx of the entire equation here, e to the xy plus x squared minus y squared is equal to 10. So just for the derivative with respect to x of e to the xy, let's remember that this will be, all right, if u is xy, then we need du dx, which is the derivative of this exponent x times y here. So we need to use the product rule. So if we have here the product rule, the derivative with respect to x of x times y will be, all right, just xy. All right, I don't want to use too many u's, but so I'll do this off to the side. All right, u is x, v is y, u prime or du dx will be 1, and v prime or dv dx would be y prime dy dx. So this is y plus x dy dx. All right, so this is e to the u du dx, or e to the xy times y plus x dy dx. So this derivative becomes e to the xy times y plus x dy dx. Then plus the derivative of x squared, which is 2x, minus, right, the derivative of y squared, which is 2y dy dx, equals the derivative of 10, which is 0. All right. So now we will need to distribute the e to the xy. So we have y e to the xy plus x e to the xy dy dx plus 2x minus 2y dy dx is equal to 0. So here's dy dx, dy dx. So let's subtract the y e to the xy from each side and the 2x from each side so that we get only the terms with dy dx left on the left side of the equation. So we have x e to the xy minus 2y, all right, times dy dx. So we can factor out the dy dx as well, and that it will be equal to negative y e to the xy minus 2x, then divide by x e to the xy minus 2y on each side to get dy dx. So dy dx is negative y e to the xy minus 2x all over x e to the xy minus 2y. What a time to be alive. All right, so now let's do another example here. Let's find an equation of the tangent line to the graph at the given point. So the equation of the tangent line again is y minus y1 is m times x minus x1. And here is x1 and y1. All right, so of course there are a couple of ways to do this, but in either case you need to find the slope. M is f prime of x, the slope of the tangent line. So we need to here use the product rule. So u is x, v is e to the x, u prime is 1, v prime is e to the x, and then we need the derivative of e to the x. So this will end up being e to the x. So if we use the product rule, we have 1 times e to the x plus x times e to the x minus e to the x. The e to the x is 0 out, so I have x e to the x. And then if I want the slope of the tangent line at x equals 1, I have 1 times e to the 1, which is e. So here's the equation of the tangent line, y minus y1, which is 0. The slope was e, so m is e in this case, times x minus x1, which is 1 in this case. So y is equal to ex minus 1, or if I distribute the e, y is ex minus e. What a time to be alive. That is all of the examples for this section on the natural logarithmic function and its properties. I hope that you enjoyed this video and that you're already looking forward to the next one. Thank you and have a great day.